back. Today we're going to be exploring a very interesting idea about differential operators of fractional order. Before we dive into the fractional order side of operator theory, let us first view differential equations and integral equations from the perspective of differential operators. So for the beginning of this discussion, I'm going to be using the notation dx of something, hopefully a differentiable function, as synonymous to the notation d over dx of, again, some differentiable function. So, from the perspective of single variable calculus, if you see the differential operator applied on one could view this as a vector or a function of x squared plus 5x plus 2, using your typical limit definition or infinitesimal definition of derivatives, one can of course find this to be 2x plus 5. So one very important property of ordinary differential operators is that if we have the differential operator of y to be equal to 0, one can easily verify that y equals 0 is a solution to this operator equation. But the very important question is this the only one that satisfies this? No, of course not. Everyone should know, if they've taken single variable calculus, that if the derivative of some differentiable function is equal to 0, then this is only true as long as y is a constant function, right? So one can view this, at least from the perspective of linear algebra, that the null space of this differential operator, which in some case can be viewed as a matrix, is not just the 0 vector or the 0 function in this case. And since the differential operator does not only have the 0 vector in its null space, that means that this operator or matrix is not a one-to-one operator. And this is going to be very, very important for some of the concepts that I'm going to be talking about today. So, if it's not one-to-one, how would one even begin to define the inverse of this operator? So if we define this operator, which I'm going to denote as d to the minus 1 of x, and obviously if it is an inverse operator in any sense, it has to satisfy at least one property, and that property must be that the derivative of the inverse derivative of y, this hopefully should be equal to y. If this is the case, then we should be aware, that since dx is not a one-to-one operator, then dx inverse is multivariate. Right? So if we just define, for example, the inverse derivative in the typical way, in particular like antiderivatives and indefinite integrals, for example, dx inverse of 2x plus 5, then we would like this to be hopefully, x squared plus 5x plus 2, x squared plus 5x plus 3, and several other answers could be the answers to this question, right? Generally speaking, x squared plus 5x plus c. That's usually what we refer to as the general solution of that expression. And this object here, this c, that's obviously the null space of this differential operator. Trivially, right? Because that's what goes to 0 when you differentiate it, right? And this non-one-to-oneness property of the differential operator is why the expression dx inverse of dx of y is not necessarily equal to just y. So defining inverse operators on non-one-to-one operators does pose a little bit of difficulty. But there are a couple ways that one could go around this particular thing. So how could one define an inverse operator of the differential operator that produces one value, not many? So one way we can do this is we can define this operator dx inverse in a different way. So we can define it as dx inverse, and let's assume we're applying it on some, let's say, integrable function. We can define this to be the integral from a to x of f of t dt. So if we know that capital F is an antiderivative of little f, i.e. the derivative of capital F is equal to little f, then this will just be equal to f of x minus f of a, right? And keep in mind this is just a single function, not many, right? So obviously if that's a single function and not many, then we have that dx inverse maps one function to a unique function, and in particular the derivative of one function will be mapped to a unique answer as well. So this gives us some nice one-to-oneness in terms of, or partial one-to-oneness, I guess you could say, of derivatives and inverse derivative operators. Agreed? And again, where this particular thing is equal to that thing. Okay, so now that we've sort of discussed this from the operator perspective, let's actually take a closer look at differential equations and what we've actually been doing. So differential equations. So what is a differential equation? So we state that the derivative of some unknown function is equal to some function, hopefully it's smooth enough, say sine x over x plus e to the minus 5x minus x. And we're like, okay, well, what is y equal to? So y, at least from the general perspective of classical differential equations, we would just take the antiderivative or find the indefinite integral of the function sine x over x plus e to the minus 5x minus x with respect to x. And we're going to be like, oh, well, that's just going to be equal to the sine integral of x minus 1/5 e to the minus 5x minus 1/2 x squared plus some arbitrary constant c. Right? And usually what we do is we call this the general solution of the differential equation, right? So this is going about it in the perspective that, differential operators are not one-to-one, because we're including the null space of the differential operator as part of the solution to that differential equation. But there are other ways you could go about this, because we can say, okay, well, y can be defined to be equal to the integral from 0 to x of the sine of t over t plus e to the minus 5t minus t dt. So we can define this as the solution of the differential equation. And notice I'm saying the solution, so I'm in some sense hinting at a particular solution. Because what will this be equal to? So that's just going to be equal to the sine integral of t minus 1/5 e to the minus 5t minus 1/2 t squared. But then we would just have to evaluate this as t goes to x and as t goes to 0. So when we do that, what are we going to have? Well, we're going to have sine of x minus 1/5 e to the minus 5x minus 1/2 x squared, which is the same part as the front of the solution. And then we're going to have minus psi of 0 minus 1/5 e to the minus 5 times 0 minus 1/2 0 squared. So we know that the psi of 0 is going to be equal to 0, 0 squared is going to be equal to 0, and this is just going to be equal to minus 1/5. So once we simplify this, what we're going to have is just psi of x minus 1/5 e to the minus 5x minus 1/2 x squared minus 1/5. And one can say that that is equal to y. But from the perspective of differential equations, this would not be viewed as the general solution. Usually we refer to this as the particular solution of the differential equation. And you're like, well, how would I get some of the other solutions or particular solutions of the differential equations? Well, all we would have to do is just change that lower bound from 0 to something else, like 5 or 6 or 7 or 8, or maybe even minus infinity. Hopefully this converges at minus infinity. In some sense, it's hard to say that because e to the minus 5x goes to infinity there. But generally speaking, that will generate a series of particular solutions, which altogether would form the general solution of that differential equation, right? So these are just two perspectives from the operator theory perspective, of where you have one perspective where it's totally reliant on the lack of one-to-oneness property of differential operators, and one that sort of takes into consideration that maybe we can define a subset of that, a non-one-to-one operator, such that the inverse of that operator produces a unique answer, which some of us usually refer to as the particular solution of the ODE. Now that we've taken a look at differential equations from the perspective of differential operators, now let's take a look at integral equations from the same exact perspective. In particular, let's start off with a very basic integral equation. The inverse derivative of x of some unknown function y will be equal to x squared plus 5x minus the absolute value of x. And let's assume we want to solve this integral equation for y. So what is the inverse of the inverse operator of y? Well, that's obviously going to be the differential operator. So if we want to solve for y, then what we're going to do is we're going to just multiply both sides of this equation by dx. So we'll have dx of dx inverse of y will be equal to dx of x squared plus 5x minus the absolute value of x. And obviously x cannot be equal to 0 here because the absolute value of x is not differentiable there. So we've already justified that the dx of dx inverse will be equal to just the identity mapping. So that's just going to be equal to our solution y. And over here we're going to have what? So we already know that differential operators are linear, so the derivative of x squared would be equal to 2x, derivative of 5x will be equal to 5, and the derivative of the absolute value of x function will be the absolute value of x over x, and that will give us the solution to the original integral equation. So obviously integral equations are much more nicer to deal with because we have this property that the derivative of the inverse derivative of y is equal to just that function y. But differential equations has that one-to-oneness property to sort of deal with, where we have that plus c function, which is associated to the null space of dx. So what happens when you start mixing derivatives and integral equations together? That's what we get, in particular, in differintegro equations. So differintegro equations, that's where we mix derivatives and integrals together. Or you have both inverse and derivative operators in the same exact equation. So let's do an example of differintegral equations and their solutions. Let's do the derivative of y plus the inverse derivative, aka integral of y, will be equal to the hyperbolic sine of x. With the initial condition that y 0 is equal to 2. Now we need this initial condition in order to get one solution due to the non-one-to-oneness property of dx, right? Because when we anti-differentiate that, that's going to give us a family of solutions, since the null space is non-zero. But if we just had an integral equation, we wouldn't need an initial condition to give us that unique solution. So let's use some properties of the Laplace transforms here, and let's do the Laplace transform of the differential operator of y plus the Laplace transform of the inverse differential operator of y, and that's going to be equal to the Laplace transform of the hyperbolic sine function of x. So we've already proven that the Laplace transform of the differential operator will be omega times the Laplace transform of y minus the initial condition at 2, and then plus 1 over omega times the Laplace transform of y, and that's going to be equal to 1 over omega squared minus 1. And then I can solve this equation for the Laplace transform of y. So it's going to give us omega plus 1 over omega times the Laplace transform of y will be equal to 1 over omega squared minus 1 plus 2. And then I can get a common denominator here of 1 plus 2 omega squared minus 2 all over omega squared plus 1, which is just going to cancel to 2 omega squared minus 1 over omega squared minus 1. Over on the left-hand side, I'm going to get a common denominator of omega, and that's going to give us omega squared plus 1 on the left-hand side. So we have omega squared plus 1 over omega. So in some sense, you can view this as a second-order differintegral equation. And on the right-hand side, we're just left with 2 omega squared minus 1 over omega squared plus 1. And then we can multiply both sides by the reciprocal of that leading rational function to get Laplace transform of y by itself. So we have the Laplace transform of y will be equal to what? So 2 omega squared minus 1. Then we're going to have that omega there. Then we're going to have omega squared minus 1. And then omega squared plus 1 on the bottom. And once we perform some partial fraction decomposition on this expression, what you're going to have is 1/4 all over omega minus 1 plus negative 9/4 omega plus 1 plus 1/2 all over omega plus 2 squared plus 2. And then we can invert each of these functions because we know the inverse Laplace transform of every single one of them. So we have that the solution to our second order differintegral equation will be equal to 1/4 e to the x minus 9/4 e to the minus x plus 1/2 omega plus 1 squared. So what's that going to be? Well, that's just a shifted transform of x, that's going to be x e to the minus x. And then over here we have a direct delta function of 2 delta x, and that will be our solution to our second order differintegral equation. Now that we know the basics of differintegral equations, let's do a quick example of higher order differintegral equations. What we have here is a second order derivative, a first order derivative, the zeroth order derivative, which can be viewed as the function itself, the inverse derivative, a second inverse derivative, which can be viewed as the first integral and second integral of a function respectively, and over here we have just a inhomogeneous term of 1. And over here we have two initial conditions, y0 and y prime of 0, which are both needed because we have these non-one-to-one operators, d and d squared. So since we have a second order differential equation in disguise, we need two initial conditions in order to produce an exact solution. In terms of nomenclature, since we have a second order derivative and a second order integral operator in the same exact equations, we would in some sense add these two numbers together in absolute value, and we would say that this is a fourth order differintegral equation, or one can say a 2 plus 2 order differintegral equation with derivative order 2 and integral order 2 respectively. So I've just chosen an initial condition of y and y prime both to be equal to 0 for simplicity, but theoretically these could be anything else, but I just want this example to be quite nice in solutions. So once I take the Laplace transform of both sides of this differintegral equation, I'm going to have omega squared minus omega plus 7 plus 1 over omega plus 6 over omega squared times the Laplace transform of y, and that's going to be equal to the Laplace transform of 1, which we know to be 1 over omega. From here, I'm going to get a common denominator for my interior fraction, and that's just going to give us omega to the power of 4 minus omega to the power of 3 minus 7 omega to the power of 2 plus omega to the power of 1 plus 6 times omega to the power of 0 all over omega squared times the Laplace transform of y, and that will be equal to 1 over omega. Once I multiply both sides by omega squared, one of those omegas will cancel with each other, and we're just going to be left with 1 omega on the top, and then we're going to have this quartic polynomial on the bottom, which actually factors quite nicely. So once you factor that out, you're going to have the Laplace transform of y will be equal to omega divided by omega minus 3 times omega minus 1 times omega plus 1 times omega plus 2, which you can easily get using the rational zeros theorem for polynomial factoring. Once I do a partial fraction decomposition of this, you actually get some quite nice numbers here. So this is obtained by partial fraction decomp, but you're going to have a system of 4 by 4 equations, which isn't too bad since all of our roots do not repeat. So that's actually going to come out to 3/40 over omega minus 3 plus negative 1/12 over omega minus 1 plus negative 1/8 all over omega plus 1 plus 2 over 15 all over omega plus 2. So once you have those decompositions and you know the inverse Laplace transform of those four expressions, then you have your 4 independent solutions. So in some sense, if you have a degree n differintegral equation, you're probably going to be looking for n independent solutions, similar to higher order differential equations. So for our solution for our differintegral equation, we have y of x is equal to 3/40 e to the 3x minus 1/12 e to the x minus, not plus, minus 1/8 e to the minus x plus 2 over 15 e to the minus 2x, and that will be your solution to this 2 plus 2th order higher order differential equation. And again, I just want to mention this little subtle theoretical property that we probably clearly see. Let's assume we have d of m of y plus dm minus 1 of y all the way down to the 0th derivative of y, which is itself, plus the inverse derivative of y, plus all the way out to d minus n of y. Let's assume this is equal to 0. So what are we going to be looking for? So we're going to be likely, I'm going to say likely because I'm not proving it here, to be looking for m plus n independent solutions, right? And possibly a particular solution, but since we have a 1 in the original inhomogeneous equation example, in some sense it's possible that that combines into the other 4 in our case, right? But I'll let you investigate the theory behind this general equation on your own, but the results are actually quite interesting if you desire to explore that route. So the next question that we want to answer is actually the biggest question of this discussion. Can we extend this differential operator or potentially integral operator with alpha in the set of integers, because we've already discussed how to do it for natural numbers and negative natural numbers and also 0. Can we extend that to the entire set of real numbers? That's the important question. If we are to do that, obviously we want this operator to satisfy at least some minimal properties for at least to coincide with the natural classical derivative. So that would be the first requirement, that the alpha derivative of a function should be equal to the natural analog of that derivative for alpha in the set of natural numbers. We would also need an identity operator. So we would like the 0th order fractional integral or fractional derivative to be equal to the function itself, i.e. a 0th order operator. And then we have the opposite, and here you have a little bit of flexibility. That is, if we want to define an antiderivative or a fractional antiderivative, we would just do a fractional iteration of the classical integral operator, right? So this obviously would be the case, or an ideal case, for alpha in the set of natural numbers. Notice here that this is negative alpha, right? So that would be the case, right? But this formula isn't actually, nice. And also we have another issue. What about these a's? Can we choose a to be 0, minus infinity, anything we want? Usually people will refer to these as base points, but which do we choose? And in some sense, the answer is any. And if you choose a particular base point a, then we probably should subscript this differential operator with whichever base point we're actually dealing with, right? But the problem is definitely this formula does look a little bit intimidating. Maybe we can, find the natural analog of this, just replace n with alpha, and hopefully all will be well. So one theorem that will allow us to do it is the following. So let's state it here. So the negative natural derivative, or the natural integral of a function f, defined to be equal to this iteration, the integral from a to x, the integral from a to x1, all the way out to the integral from a to xn minus 1 of some function, let's say dt dx1, all the way down to dxm minus 1. This is actually just equal to 1 over m minus 1, the quantity factorial, integral from a to x, of x minus t to the m minus 1 f of t dt. And you're like, so repeated integral is just a single integral in disguise with a couple little functional modifications? Indeed, yes. At least that's what this theorem says. So let's just do a quick sketch of how you would prove this. So you could use mathematical induction to do the full proof if you desire. So if we do n is equal to 1, to sort of do it, or set up a mathematical induction, 1 minus 1 would be 0, and 0 factorial is 1. So what we're going to be left with is just the integral from a to x. 1 minus 1 is 0, and x minus t to the 0 will be equal to 1, provided the base point isn't 0, which it's not since we're going from a to x. And then we're just going to be left with f of t dt, and that's just our natural first order integral. Now the fun part is when n is equal to 2. So when n is equal to 2, is this really true? So what will we get? So we're going to have 1 over 1 or 2 minus 1, the quantity factorial, times the integral from a to x, and then we're going to have the integral from a to x1 of f of t dt dx1. Right? So what are we going to do here? So 2 minus 1 is 1, and 1 factorial is 1, so we're just left with 1 over 1 factorial. And we can write this again as the integral from a to x times of the integral from a to x plus 1. And notice that the order of integration is t first and x second. So what I want to do is I want to reverse these things, which means these bounds are definitely going to change around a bit. So once you work out that multivariable calculus transformation, what you're going to have is the integral from a to x, and then the integral from t to x, and then we're going to have f of t dx1 dt, right? So we're just doing a change of variables here. There's a change of variables. So once we have that, then what do we have? So what we have here is an integral with respect to x1, but this is just a function of t, so f of t is as far as we care, is just a constant. So we're left with 1 over 1 factorial times the integral from a to x, and then we're going to have f of t, which is just a constant, and then we're just going to be integrating x1 with respect to t and x1 once we subtract. So we're just going to be left with x minus t dt, and that's precisely what the identity, at least for us, says, because this is just 1 over 2 minus 1, the quantity factorial, times integral from a to x, and then we're going to have x minus t to the power of 2 minus 1 times f of t dt. So it definitely satisfies for n is equal to 2, and then you can extend that with mathematical induction to any natural order m. Right? So what exactly are we going to do with this? So from here, what we can do, at least from the perspective of Riemann and Liouville, is that one and or both extended this natural order definition just by replacing the natural number n with a real number alpha. So what that looked like was this. So we have a Riemann-Liouville fractional derivative of order minus alpha of some function f of x, which some people would also call a Riemann-Liouville fractional integral. So we're going to use I and then replace minus alpha with alpha of ax of some function x. And that's going to be equal to, keep in mind, 1 over n minus 1 factorial is just 1 over gamma n. So that's just going to be equal to 1 over gamma of alpha times the integral from a to x. And then we're going to have x minus t to the power of alpha minus 1 times f of t dt. So this would be the Riemann-Liouville fractional integral of order alpha with base point a. And keep in mind, at least for the domain of gamma function, on the negative integers, does not exist, including at alpha is equal to 0. So this identity only really makes sense for alpha greater than 0, right? So that's the Riemann-Liouville fractional integral. Now let's get into a couple examples to sort of see how this operator works. So since this number is not a fraction, it's just a natural number, this probably is just going to be like a natural integral of the function x, which probably is like 1/2 x squared plus c, where c is going to be some particular number. So if we use the definition of the Riemann-Liouville fractional integral, this is just going to be equal to 1 over gamma of 1 times the integral from 0 to x. So keep in mind this base point, so this base point goes here, and that's going to be our upper limit point x, which is going to be there. And then of the x minus t to the 1 minus 1 function, you can in some sense view this function as a kernel, similar like we did with linear Volterra integral equations. And then our function x in the form of t with respect to t. Now, 1 minus 1 is equal to 0, so x minus t to the power of 0 is that's just going to be equal to 1. So we're going to have 1 divided by gamma 1, which is the same as 0 factorial, times the integral from 0 to x of t dt. 0 factorial is defined to be equal to 1, so that's pretty nice. And then we're going to have 1/2 t squared, and then we're going to evaluate this as t goes to x and as t goes to 0. Notice that if this base point is changed from 0 to some other number, you're going to have some other constants. But since it's equal to 0, we have the very friendly function 1/2 x squared, which is the intuitive answer for what we should get. So that example is not too bad. So let's look at the second one. So the Riemann-Liouville fractional integral from 0 to x of order 2 of the same exact function. So this is going to be equal to what? So this is going to be equal to 1 over gamma of 2 times, again, the integral from 0 to x of x minus t to the 2 minus 1, and then same function t dt. So 1 over gamma of 2, that's going to be equal to 1 factorial, which is going to be equal to 1, times the integral from 0 to x of x minus t to the power of 1 times t dt. And then we're just going to distribute that t in, and that's just going to be equal to 1, which is pretty nice. So what we have here is the integral from 0 to t of xt minus t squared dt. And keep in mind, this is a t integral, so x is a constant as far as this integral is concerned. So this is going to be equal to what? So this is going to be equal to 1/2 xt squared minus 1/3 t cubed, and then we're going to be evaluating this as t goes to x and as t goes to 0. So as t goes to x, we're going to have 1/2 x times x squared minus 1/3 x cubed, and then what we're going to have is minus 1/2 x times 0 squared minus 1/3 0 cubed. That entire last term is going to be equal to 0, as we probably already know. And then here we have x cubed, and we have 1/2 minus 1/3, and that's going to be equal to 1/6 x cubed. And that is the second order Riemann-Liouville fractional integral of x. So does that really make sense? Well, if we think about this from the perspective of integrals, and let's do this in a different color, the integral of x is equal to 1/2 x squared. Let's forget the plus c for a moment, and if we integrate 1/2 x squared with respect to x, that's going to be equal to 1/2 times 1/3 x cubed. Let's forget the c for a second, and that obviously is your 1/6. So this is actually not really 6, but it's actually 3 factorial. So what we want to do is just write that as 1 over 3 factorial times x to the power of 3. And this gives us some room for generalization of any power, right? So let's do this. Let's do the Riemann-Liouville. Let's do order m now, 0 to x. And let's do any monomial term x to the power of m. So using this idea, that's just going to be equal to what? So notice that in order to go from 1 to 3, all we do is add 2. So that generalization is pretty trivial. So that's going to be x to the power of n plus m all over n plus 1 times m plus 2 all the way down to n plus m. But that sequence of products isn't very nice. So what we want to do is multiply by a clever form of 1, because we can multiply by n minus 1 all the way down to 1. And then the bottom is just going to be an n factorial. And since we did it to the bottom, we're going to do it to the top also. So n times n minus 1 all the way down to 1. So we see that that's just going to be equal to n factorial all over n plus m factorial times x to the m plus m, which we can extend via gamma functions quite easily as gamma of m plus 1 all over gamma of n plus m plus 1 times x to the n plus m. So using our Riemann-Liouville extension, all Riemann-Liouville does is extend factorials with gamma functions. And since this is just a Riemann-Liouville integral in disguise, what we have is the generalized power rule for integrals in the Riemann-Liouville space as the mth order. Let's actually go to alpha now, since we're going to be doing real numbers, of the monomial term, xm. This is just going to be equal to gamma of alpha plus 1 all over gamma of, let's do n plus alpha. Actually, no, that should be n plus 1, not alpha. N plus 1, and then n plus alpha minus 1 times x to the n plus alpha. So this would be the power rule for Riemann-Liouville fractional integrals, and it should be noted that this is only valid for alpha bigger than 0. So now let's do our first fractional integral of the function x. And obviously this is x to the power of 1. So using that identity that we just in some sense proved, this is just going to be equal to gamma of 1 plus 1, which is going to be equal to 2, all over gamma of 1 plus 1/2 plus 1, and then times x to the 1 plus the order, which is 1/2. So once we simplify, this is just going to be equal to gamma 2 all over gamma of 1 plus 1 is 2 plus 1/2, that's going to be equal to 5/2 times x to the power of 3/2, right? So we just increase the power of 1 by a half. Using some identities for the gamma function, because as you probably already know, gamma of natural numbers are just natural numbers, and gamma of half integers in some sense are just multiples of the square root of pi. So using some identities that you may or may not know, you can also do numerical approximations if you prefer. This actually has a nicer representation of 4 divided by the square root of 3 square roots of pi times x to the 3/2, and that's probably a nicer answer if you are familiar with some of those gamma identities. So that gives us some tools for doing fractional integrals, at least in the Riemann-Liouville sense. So now what we're going to do is we're going to define a Riemann-Liouville sense fractional derivative. because we would like these at least to be inverses of one another. So we're going to define this as the inverse of the the Riemann-Liouville fractional integral, right? So if I want to define the Riemann-Liouville fractional derivative of alpha, and still that base point would still have to be 0 if we were to extend it, then this would be equal to what? So that's going to be equal to gamma of n plus 1 still, because that doesn't depend on alpha. And over here we're going to have gamma of n minus alpha plus 1, and then x to the n minus alpha, right? And that would be your power rule for Riemann-Liouville fractional derivatives. So let's just do a quick example of that. So what would be the Riemann-Liouville fractional derivative of order 1/2 with base point 0 of the function x? So by definition, that's going to be equal to gamma of 2 again, all over gamma of 1 minus 1/2 plus 1 times x to the 1 minus the order 1/2. So that's just going to be equal to gamma of 2, which we know is 1 factorial, which is 1, all over gamma of 1 plus 1, which is 2, and 2 minus 1/2. That's going to be equal to 3/2. And then over here we have 1 minus 1/2, which we know to be equal to 1/2. So if you don't know any gamma identities, then that would be perfectly fine. But using some other simplifications, one can find that this is actually equivalent to 2 divided by the square root of pi times x to the 1/2, and that probably would be a more preferred answer for those of you who do know some identities for the gamma function. Now, I just want to mention just a couple analytical properties of Riemann-Liouville fractional integrals and derivatives that are very important for you to know, and the first is the following. I'm going to post these from the integral perspectives because they're a little bit more easier to deal with. So the Riemann-Liouville fractional integral of some base point a of x of a constant times some fractionally integrable function f. This is going to be equal to c times the Riemann-Liouville fractional integral of order alpha base point a of x of that function c of x. So Riemann-Liouville fractional integrals, constants still can factor out of them, so that's a pretty nice property. And the Riemann-Liouville fractional integral of order alpha base point a of x of the sum of f of x plus g of x. This is equal to, you might be able to take a guess, but the Riemann-Liouville fractional integral of order alpha base point a of x of f plus the Riemann-Liouville of order alpha base point a of x of g of x, and that will be your answer. So constants can factor out of that, and Riemann-Liouville fractional integrals can distribute over addition of functions. And similar for DRL, AX alpha operators. So what does this mean about IRL and DRL? So that means IRL alpha AX and DRL alpha AX are linear operators, right? So since we've already in some sense proven the power rule for Riemann-Liouville fractional integrals and Riemann-Liouville fractional derivatives of polynomials, now keep in mind those polynomials were defined for base point a equals 0. In some sense you could do base point 0 fractional derivatives and integrals of any polynomial that you desire. Now to close this video, I don't think it would be appropriate in a differential equations series to not mention fractional differintegral equations, because we've already been able to solve differential equations, integral equations of any order. So let's just solve any differintegral equation of any real order, at least for a special case of functions, in particular the polynomial functions. So fractional differintegral equations, sometimes abbreviated by FDEs. There are so many different ways we could go about solving them, because it also depends on the operator that we're dealing with. So let's assume that we have a fractional differential equation of Riemann-Liouville type with base point 0 of x of 1/3 of some function y, and that's going to be equal to x squared plus 5x minus 2. Right? So let's assume that this is our equation. So what is the inverse operator of a Riemann-Liouville fractional derivative? That's obviously going to be a Riemann-Liouville fractional integral. So the solution, at least in implicit form, is going to be equal to the Riemann-Liouville fractional integral of order 1/3 with base point 0 of x of x squared plus 5x minus 2. So again, it's very easy to prove that we can distribute Riemann-Liouville fractional integrals over addition. So we're going to get the following expression. So y of x is going to be equal to, so that's going to be what? So that's going to be gamma of 3, let's work on our x squared first, all over of gamma 2 plus 1/3 plus 1 times x to the 2 plus 1/3. Now let's move to our 5x. So we're going to have 5 gamma of 2 all over gamma of 1 plus 1/3 plus 1 times x to the 1 plus 1/3. And then over here we're going to have minus 2 times gamma of 1 all over gamma 0 plus 1/3 plus 1 times x to the 0 plus 1/3. So once we simplify that out, that's going to give us what? Y of x will be equal to 2 all over gamma of 10/3 times x to the power of 7/3, and then plus 5 over gamma of 7/3 times x to the power of 4/3, and then minus 2 all over gamma of 4/3 times x to the minus 1/3. Question: do we include a plus c here, or in some sense a function there? So if this is the case, well, how would we actually know? So this goes back to the very first point that I made at the beginning of this video. So this is equal to 0 only if the null space of this operator D0x 1/3 of Riemann-Liouville type is equal to the 0 function only. But if there are other functions in the null space of a Riemann-Liouville fractional integral of order 1/3 with base point 0, then whatever those functions are would be included there in that plus c of x term, right? Now, let's actually explore this just a tad bit before we end this discussion. Is it possible that plus c should be there, right? So let's look at the fractional derivative of order 1/3 of a constant. Let's actually see if it should be there, just to see. So keep in mind, this is a linear operator, so we can factor that c out. So we can write this as c times the Riemann-Liouville of order 1/3 of 0 to x of 1. And that 1 we can actually write as x to the power of 0. So x to the power of 0. So if we apply that power rule again, this is just going to be equal to c times gamma of 0 plus 1 all over gamma of 0 minus 1/3 plus 1 times x to the 0 minus 1/3, which is just going to be equal to c all over gamma of 1 minus 1/3, that's going to be equal to 2/3 times x to the minus 1/3, which we can write in another way as c divided by gamma of 2/3. And why am I writing square roots here? It should be gamma of 2/3, and that's just going to be the cube root of x. So that is the Riemann-Liouville fractional 1/3 derivative of a constant, which obviously is not equal to 0. So should it be plus c at the end of our differential equation? Obviously no, right? So that means that the constant functions, and let's assume that it's not the 0 function, right? So the constant functions not equal to 0 do not belong to the null space of this operator. We can actually generalize it quite easily, at least for base point 0 of x, right? So who is in the null space of this operator? Is it the only 0 function? I'll leave that question for you to explore on your own, or later when we actually explore fractional differential equations in more detail. But for now, I think that serves as a good foundation for the exploration of fractional order differintegral equations. Hope you enjoyed this video, and I'll see you in the next one. Take care.